This poster is about the constraints on RG flow from protected operators and is based on a paper published in September 2024 with Florian Baume and Elli Pomoni, Hamburg University and DESY. And the idea is to track a special operator along RG flow. In the past, people studied the stress tensor and conserved current, and from the study of the two-point function of stress tensor and conserved current, people could prove the C theorem in two dimensions, which is the statement that the difference between the UV and the infrared central charge has to be greater than zero, and the K theorem, which is the statement that the difference between the UV and the infrared two-point function coefficient of the conserved current in two dimensions has to be greater than zero. Some rules were also provided for higher dimensional cases, and the C theorem was generalized in 3 dimensions to the F theorem and in 4 dimensions to the A theorem. Our idea is to study protected operators along RG flow, and the protected operators has the property that the conformal dimension in the UV and the infrared is the same. So the two-point function of those operators can be written in this form, where C is in general is a complicated function, which has the property that when x goes to 0, this function is just a constant, and when x goes to infinity, this function is also constant, so that the conformal dimension of the operator is the same in the UV and the infrared. The main result is contained in a sum rule, which compute the difference between the UV and the infrared value of the two-point function coefficient, and the theory-dependent information enter this equation through the two-point function between the two operator O. And in particular, it's interesting to study this sum rule in the cases in which the dimension of the operator is integer and the space-time dimension is even, because those are associated to conformal anomaly, and in particular associated to type B conformal anomaly, which are related to logs in correlation function in momentum space in the CFT. We can combine the sum rule with the spectral decomposition, which is a decomposition of the two-point function in terms of three massive propagator, weighted with theory-dependent quantities entering this function, which is the spectral density. The spectral density is positive indefinite, but this will not allow us to conclude that the difference delta C is greater than 0. However, one can conclude that only multi-particle states enter the sum rule, while single particle states will vanish. And it's particularly interesting to study the sum rule in the supersymmetric case, in which the conformal manifold contains 3 points. This is because the conformal anomalies associated with this two-point function coefficient has to be covariantly constant along the conformal manifold, and therefore it's enough to study the theory close to the 3 point. So this will allow us to hint that the difference between the UV and the infrared value of the two-point function has to be greater than 0. We tested our prediction in specific example, like the mass deformation of 3 scalar theories in different dimensions, or the mass deformation of 3 Majorana fermions in 2 dimensions, but also in n equal to 2 SQCD in its X phase and some holographic RG flows.